Namaste, I am Rohan Majankar, and in this video we will be dealing with differential equation, and you can contact me at the email address given above. So now let's start. We will start with the simple concept of differential equation and what is differential equation and how to recognize the differential equation. If we have a derivative term in an equation, then it is called differential equation. And a simple definition is a differential equation is an equation that contains one or more functions with derivative, and basically we use the differential equation in economics to analyze the time path of variables under the continuous time frame. It means that if we want to analyze the time path of variable under continuous time frame, means 0 year to 5 year on a continuous basis, means that we will not take year 1, year 2, year 3. We will take the continuous series, means 0 to in the form of days or in the form of minutes, seconds, in a continuous term. Then we will use differential equation, and if we use year 1, year 2, year 3 or in a discrete series, then we will use difference equation. This is the simple difference between these two concepts. And in the differential equation we use derivative. In difference equation we use the lag or lag form of the equation, means that we will use t plus 1 for the preceding time, and t minus 1 for the previous time period, and t for the present time period. And here are some of the examples of differential equation. You can go through it. And first is, it is the differential equation of homogeneous form. It is of first degree because here it's 1 and it's 1, so it is first degree. And it is homogeneous because our variable is, or the right hand side is 0. Second is also first order because its order is 1. And it is not homogeneous because in the right hand side it is 3, not 0, so it is not homogeneous. In the example 3 we have a second order differential equation. It is second order because we have 2 and we need here write 2. It is of second order derivative. The equation 3 contains second order derivative, so it is second order differential equation. And it is not a homogeneous because the right hand side is not 0. If it's 0, then it is the second order differential equation, or it is second order homogeneous differential equation. And the fourth example is, it is also second order because it contains second order derivative, and it is of variable term because we have here t, so it is of variable term. It has a time factor in the right hand side. After going through these examples, then we will learn to solve the differential equation. In order to solve the differential equation, we can divide the whole differential equation into two parts, that is in the part of particular integral and complementary function. The particular integral gives us the equitemporal equilibrium, means that if the time series is convergent, then up to which point the time series converges, it is given by the particular integral. And the complementary function means that it gives the time path. It gives that it tells us that whether the time path is convergent or divergent, or whether the time path will have a swing, means oscillation, or it will not have oscillation. This is given by our complementary function. So now simply moving towards our example, let us take the differential equation dy by dt plus 3y equals to 3, where y0 equals 6. It is given. I have taken it as equation A. It is the first order differential equation because we have first order derivative in this equation in the form of dy by dt, and it is non-homogeneous because this point, sorry, it is non-homogeneous because here is it's 3 not 0. If it would be 0, if this would be 0, then it would be homogeneous. Currently it is not 0, so it is a non-homogeneous differential equation of first order. So moving towards our solution, we will have method 1 and method 2, and in method 2 we will find out the particular integral. First we will find out particular integral, and we will let y equals to k. K is our arbitrary constant, and we will differentiate y with respect to t. Since k is constant, the derivative of k is 0. dk by dt equals 0, and when we replace the value of y and dy by dt in our equation, in our above equation, in this equation, then we will find, or we will get the value of yp is 1. And similarly for the complementary function, let y equals to aert, which is not equal to 0. We will let it not equal to 0, and we will differentiate it with respect to t, and we will get arert, because differentiation of aert is arert, and we will replace the value of y and dy by dt in our equation A, and we will solve for r, and we will obtain the value as yc equals to ae minus 3t. And here I have written the footnote why to take aert, y equals to aert, and you can go through this footnote. And now for yt equals to yc plus yp, yt equals to ae minus 3 plus 1 is a general solution. For different solution, we will replace the value of y0 equals to 6 in our general solution, so we will get the value of a equals to 5. So our different solution is yt equals to 5 e minus 3t plus 1, and we must analyze our time path. Since r is less than 0, the time path is convergent without oscillation. It has no oscillation because there is no any component such as sine or cos that causes oscillation. And since our value is since our complementary function is 5e minus 3t, the time path is itself convergent. Why is so? Then minus 3 minus 3t, we can write this equation in the form of e minus 3t, and if t increases, the et will approach to infinity, and 5 by infinity equals to 0. So we can say that this whole equation is convergent towards 1. It's converged to 1. And here is method 2. You can have a look over the PDF file. Thank you.